let's see. So we just invited our buddies from the border into our space. Welcome, direct normalizable functions. Thank you, thank you, thank you. All right. And then postulate number 2. Observables are represented by permission operators. A determinate state for an operator Q determinate means having a well-defined value of the observable. You're guaranteed to get the same result every time you measure on an ensemble. A determinate state for an operator Q is an eigenstate of Q. Or in other words, Q applied to the state vector should be some eigenvalue times the state vector. So the state vector has to be an eigenstate of the operator Q for it to be a determinate state. And what does that mean? It means a measurement of Q, which doesn't literally mean measure the operator, it means measure the physical quantity associated with it. A measurement of Q on a determinate state is guaranteed to yield the eigenvalue Q little q. Mean by determinate. It's got a well-defined value of that observable. You're guaranteed to get a specific result, namely that eigenvalue. Question. Why permission? Why do we want permission operators? Because their eigenvalues are real. Yeah, because their eigenvalues are real. We want real eigenvalues. We want to be keeping it real. Because we have yet to make a measurement of, say, some momentum and found out, oh, look at that, it's 4 + 7i kilogram meters per second. Postulate number 3. Nobody's ever proved this for all permission operators. But on the other hand, if it isn't true, quantum mechanics wouldn't be consistent, so therefore it's probably true. Or quantum mechanics is wrong, one of the two. Which is the eigenstates of the operator representing an observable span the Hilbert space. In other words, they form a basis. They form a complete set. You can represent any element of the Hilbert space as a sum over those eigenstates. Eigenstates of an operator. Oh, wow. What is that? An operator. I can't even pronounce it. An operator. An operator. Wow. Okay. The eigenstates of an opera. Hello. Yeah, the eigenstates of an operator representing an observable spanning the Hilbert space. I'm psi 1, I'm psi 2. You know, there's these eigenstates of an opera. Of an observatoire. All right. All right. Did I tell you I've had 4 hours of sleep? An observable span Hilbert space. Okay, fake break time. Span the Hilbert space. Set of eigenvalues of an operator is called its spectrum. And by analogy with the spectrum of light. For a discrete spectrum, or in other words, if Q, I'll call them, okay, I'll just keep what I did in my notes. Q Fn is equal to some eigenvalue Q sub n Fn with n a countable index. You can label them with integers, in other words. Countable just means they could be labeled with integers, like, for example, the eigenstates of the infinite square well, the eigenstates of the harmonic oscillator. We could label them with n equals 0, 1, 2, 3, etc. for the harmonic oscillator, n equals 1, 2, 3, 4, etc. for the infinite square well. Those would be examples of that. For an arbitrary state vector psi, we have that the state vector can be written as a sum of the Cn f sub n. That's what we mean by the eigenstates span the space, as some linear combination of them can be used to represent any state vector. That would bring in, Alex pointed out, Hilbert space is what is it? The set of square summable sequences. Well, this is a square summable sequence. We're adding an infinite number of terms in order to get our state vector there. With C sub n being the inner product of psi with f sub n. We can do that. How would we derive that? Well, you take the inner product of both sides with f sub m, and then use the fact that the f sub n and m's have a Kronecker delta normalization. In other words, the normalization of the states is that the inner product of Fm and Fn states is delta Mn. The Kronecker delta symbol is what applies there. 0, they're orthonormal to one another, so the inner product is 0 if it's two different states and 1 if it's the same state. Right? So we would derive this by, I'll just mention it, if I go like this, Fm psi would be the sum over n, Cn Fm Fn equals the sum over n of the Cm delta Mn, but that means only one term lives, and that's C sub m, and so C sub m is the inner product of psi with Fm, and here I just renamed it back to n again for the index. So that's what happens if you have a discrete spectrum. If you have a discrete spectrum, the states are normalized to the Kronecker delta. You sum over them to represent a discrete summation to represent any element of the Hilbert space. And that's the formula then to find out the coefficients in the expansion. For a continuous spectrum, where we've got Q applied to a state labeled with Z, f sub z, equals some function of z times f sub z. So eigenvalue as a function of z times f sub z. So here's a case where we can't label the states with an integer index. We've got a continuous index. There's a state for every value of z which form a continuous set of possibilities. Then this would be the situation that you get with z, a continuous index. There's a value for every real z, not countable. In that case,
so why is Q a function of z?
well, because the idea is we have to label, I could call this Q sub z if I liked. I could have called this Q sub z, just like over here. I called this Q sub n. The point would be that Q sub z has values for every real z, at least in some interval between some value z1 and z2 or something. Well, if I have something which has a value for every value of z in some range, maybe from minus infinity to infinity, that's a function of z, isn't it?
But is it, yeah, I get that part, but is it necessary that Q is a function with z exists in it? Like
Well, yeah, well,
variables in Q.
I'm claiming, well, see, I'm saying that if there is a continuous spectrum, then the states have to be labeled by some continuous index. So, for example, it might be for the momentum operator, there's an eigenstate for every value of p, right? So that would be an example. In that case, Q of p is simply p itself. Q of z might just be z. It might be the eigenvalue is z, but it might be z squared. It might be sine of z or something like that. We're being very general here, in other words. Being very, very general here. For what we've already met, the momentum operator, this just becomes, we would say, p on p is little p on p. Well, that's a function of p, isn't it? That's f of p equals p, or, that's q of p equals p, if you like, or whatever. So I'm just being very general here. So this would just be an example. Then we're going to have that psi has to again be a sum over the eigenstates, but it's got to be a continuous sum instead of a discrete sum. What do we call a continuous sum? An integral. So instead of summing on the index n, we have to integrate on the index z, or in other words, it's going to be an integral dz c as a function of z f sub z. With c sub z is the inner product of psi with f sub z. So notice it's exactly the same formula as we get in the discrete case. And the idea here would be that if I take the inner product of psi with, what am I going to call it, f sub z prime, then I'm doing that integral on the other side. I take the inner product of psi with state f sub z prime on both sides. And for a continuous index, index, we want them normalizable not to the Kronecker delta, but to the Dirac delta. So this is going to be delta of what? Not z prime by itself. Two indices, z minus z prime. Yeah. In general, you've got two indices. When it's just delta of z, that's really delta z minus 0, right? It's z and 0 that are involved. But in general, it's going to be z and something else. So z minus z prime. So that'll be equal to c of, whoops, here I wanted to say c of z. I could use a subscript z here, but I'm using c of, but here I'm saying it's a function. If you use a subscript z and the subscript is a continuous index, that's a function of z. So c of z prime is equal to the inner product of psi with f sub z prime. Now I just rename it back to z again. C of z is the inner product of psi with f sub z. Eigenstate f sub z. So note that the formula in the end for the coefficients look exactly the same whether you're in the discrete case or the continuous case, because the Kronecker delta plays exactly the same role in the sum that the Dirac delta plays in the integral. That gives them exactly the same kind of formula that you get out at the end. How do you evaluate this sucker right there? You insert the identity in whatever basis you're in. In the x basis, if I want to actually evaluate that piece right there, then I insert the identity. What does this well, first of all, what does this inner product represent? Inner product of psi with x is what we call psi of x, the position space wave function. Meanwhile, what is this inner product? F sub z of x star. So to actually calculate it means to do that integral, integrate f star sub z of not of its function z as x. So in other words, integrate the wave function, which has eigenvalue z, which has eigenvalue c of z, psi of x dx. Do that integral right there. Just to see if you're following along, what would it be in the p basis? Insert the p identity. Well, notice it doesn't care what you call that variable in there. So it's got the same formula in either basis. It's just that you use the momentum space wave functions to do the integral if you're in the p basis, and you use the position space wave functions if you're in the x basis. Yes?
I have a question. Where does that extra dx come from?
Oh, it comes from me forgetting that I'd already written it right there. It comes from 4 hours of sleep. Yeah, you're absolutely right that made no sense whatsoever. Yeah. Same deal. Wow. Can't believe I didn't. Well, I can believe I didn't notice that, but yeah. Yes, only one differential allowed in a single integral. Yeah. It came because the other one was remote, so or they're like, you know, they're chaperones. They don't trust these guys seating one in the front, one in the back to be sure they don't wander off everywhere. Or I had 4 hours of sleep. Yes.
So the F, Z
Mm-hmm.
are just the eigenfunctions of.
Yeah. In other words, if in the X basis we would say the Q operator acting on F sub Z of X
Okay.
is equal to C of Z times F sub Z of X. The eigenvalue, Q of Z, sorry. Q of Z, yeah, Q of Z. The eigenvalue associated with operator Q for Z, basically.
I was just trying to relate it back to the
Mm-hmm.
Fourier side.
The Fourier business is, we made kind of the simplest case where Q as a function of Z is simply Q, is simply Z in that case, if you will. So in other words, for the P operator, we go P psi P of X is little p psi P of X. But, you know, for example, what about the P squared operator? The P squared operator has the eigenfunctions of the P operator also as eigenfunctions, but the eigenvalue of the P squared operator isn't P, it's P squared. Right? So it doesn't have to be just a simple thing there. It can be some function, like P squared, or P squared over 2m, or P squared over 2m plus your mom's weight over your dad's weight times the age of the universe over 7, or whatever, you know, whatever weird operator you want to create. So you can have some, whatever, you know, crazy function out in front instead of just like P, or whatever. And note that we could do the same expansion here and find that Cn is the same kind of integral. Cn is going to be the integral of dx f sub n star of x, psi of x, dx. It has exactly the same form, whether you're dealing with a continuous index or a discrete index. Because if you insert the identity in this expression, well, the only difference is I've got an f sub n versus an f sub z, so you're still going to get exactly the same formula as a result of that. Yes? What did I do this time? Sorry. It's going to have dy dz over the volume element dx dy dz. There, I fixed it right up for you. I just can't get over that.
4 hours of sleep. Don't worry, I know about that. Someone pulled the fire alarm at 3 a.m. in my door.
Okay, yeah, right.
It's fine.
That's not what happened with me, but yeah. Actually, what happened with me is wanting me to perfect the solutions to homework 7. So that by the time you guys got it in your hands, if you happened to run home and look at homework 7 solutions, they would be just the way I wanted them. So I stayed up in order to do that.
Oh, yeah.
So I feel better now about having gotten it done, but it's also causing me to throw extra differentials in here and there, you know, so. All right. And then we have the generalized statistical interpretation. Generalized statistical interpretation. You know this too, but let's formalize it. If you measure an observable Q on a state psi, some physical quantity associated with Hermitian operator Q, Q as a result. Ay, ay, ay. Good values of Q as a result. For a discrete spectrum, the probability of obtaining Q sub n is, see how well you remember chapter 2, is, so if I've written psi is the sum of the Cn Fn, we called it psi n before, what's the difference? Nothing. So what's the probability of getting the eigenvalue associated with that, the nth eigenstate? Cn squared, yeah, Cn, well Cn absolute square, right, is Cn absolute square. The absolute square of the coefficient, or in other words, with our understanding of how you get those things, it's the projection of the state vector, it's the absolute square of the projection of the state vector onto the nth eigenstate of the operator. It's the projection of psi onto Fn, that's what C sub n is, absolute square. So in other words, it's the Fn component of the state vector, so to speak. Square that, that's the probability of getting that result. So it's almost like, you know, if you could literally picture the state vector as an arrow, and let's say there was only 2 possible results of a measurement, then the probabilities would be this component squared and that component squared, which would add up to the length of the vector, and we normalize them so they have length 1, so the total probability is 1. So that's kind of a mental picture to have, even though we can't literally picture these state vectors as being arrows. So like, you know, if this is eigenvalue Q1 and this is eigenvalue Q2 axis, so to speak, then this is the, or no, sorry, if this is the, I should say, state 1 axis, and this is like the state 2 axis, and here is psi, then its projection, the square of its projection along state 1 is the probability of getting the eigenvalue associated with state 1. The square of its projection along state 2 is the probability of getting state 2. And you add the squares of the projections together and you get the square of the length of the vector, but that's supposed to be 1 because you're supposed to get unit probability of finding something. And so that's kind of the picture we have. Except you can't really draw that picture because they're not really pointing anywhere, but still it's kind of useful to, or at least interesting to think of it like that. Well, for a continuous spectrum, Alex is still with us. Because we got Alex in here already, I always think Russell for Alex Russell somehow. Because he's got 2 first names too, or 2 last names, or whatever, you know. So. Sorry, Alex. That's all right, Dr. Harmon. Thanks, appreciate it. All right. I'm confident that's what he's thinking right now. He's not thinking anything about that right now. He doesn't even know I said that.
Whereas it's like really lends itself to your imagination.
That's true, yes. Wow, for a continuous spectrum, the idea would be that, where did I go? Yeah, that the probability of obtaining a result in the range dq which is Q of z minus q of z equals dq dz dz, because we've said that q is a function of z. So we want a little range dq, which will be dq dz dz. Because in other words, the probability of finding z in the range dz corresponds to the probability of dq spanning dz dq dz q dz dz. Is instead of just c of z absolute square, you have to multiply by dz. You know that, psi squared dx, right, instead of just psi squared. The probability, if you got a continuous index, the probability of getting any particular value is 0. You can only talk about the range of finding the x for a particle in some little range. The probability of finding some exact value of x is 0. But the probability of finding it in some little range dx is absolute square of psi times dx. So for a continuous index, you can only talk about the probability of finding it in some little range of the index. Or in other words, again, the probability depends on the absolute square of the projection of the state vector onto the eigenfunction in question, except for a continuous index, we have to multiply by a little range of dz's to find the probability of getting it in that range dz. Or in terms of q, getting it in the range dq equals dq dz dz. Any questions? All right. Now, there's one more thing we have to throw in, and that is if I make a measurement and then make another measurement right away, what do we know will happen? If I make a measurement and then I make a measurement of the same variable again right away,
You get the same value?
you get the same value, right? You get the same value because making a measurement does what to the wave function? It makes it collapse, right? It's like, hello, wave function. Right? You make the measurement and it collapses.
Wow,
Right?
so every wave function is a house of cards.
It is pretty much, yeah. It's like, hello, wave function. Right? It collapses. Yeah. Exactly. Yeah, so the house of cards principle. So we need to bring that in too. So after a measurement, the wave function collapses. In a way not described by the Schrödinger equation. It's random, we think. Unless you're a many-worlder, in which case, I don't like your philosophy, it doesn't mean you're wrong. But in the many-worlds view, the wave function never collapses. That's its advantage. Disadvantage is I never choose coffee or tea, I choose coffee and tea. And everything else for that matter. I ride pink unicorns in some universe probably, you know. Anyway, which is kind of fun to think about. After a measurement, the wave function collapses to become the eigenstate corresponding to the eigenvalue yielded by the measurement. There's a caveat there. So you make a measurement and boom, wave function collapses to become the eigenstate corresponding to the eigenvalue. Thus, a second measurement right after the first will give the same value. That's an observed fact, is that if we measure something twice in a row over a very short interval, you get the same value. So we interpret that in terms of collapse of the wave function. That's if we're measuring the same variable. Measuring the same observable. But what if there's yes? Thank you. There we go. Okay, so what if there's degeneracy? Like what if, it's like for the hydrogen atom, right? We haven't done hydrogen yet, but hydrogen has degeneracy, right? There's the energies are determined by the principal quantum number n, but there's different values of L and M sub L and M sub S that can go with the same value of n. So if I measure the energy of a hydrogen atom, and I find that it's in the n equals 3 level, does that uniquely specify the quantum state? No, because n equals 3 can go with L equals 0, 1, or 2. M sub L for each of those L's could be minus, minus L to L in steps of 1, blah, 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 right? So in that case, measuring the energy doesn't uniquely specify what state it's in anymore. So what do you think happens in that case?
It certainly narrows down which states it
It narrows it down, but in that case, the wave function doesn't collapse to necessarily some particular eigenstate. Yeah, it collapses into some linear combination of it. In other words, it collapses onto some element of the degenerate subspace. Yeah. So, it's kind of like if I had this imaginary meter stick, and that's the wave function, and there's a degenerate subspace represented by the table here that represents any state vector lying in the table has the same value of the energy, let's say. If I measure the energy, well, first let's say that the x-axis and the y-axis on the table had corresponded to different energy eigenstates. In that case, if there's no degeneracy, I measure the wave function, and if I get the energy corresponding to this state, the wave vector collapses into that direction. If I get the energy corresponding to this set, it collapses into that direction, to this state. But if these two states have the same energy, then it just randomly collapses somewhere onto the table, some linear combination of those two states that have the same energy, and your measurement can't tell you which one. So you measure an ensemble, and you just get random places. Each state's in a different, randomly chosen element of the subspace. So that's a caveat here. In the case of degeneracy, spelled however you actually spell it, case of degeneracy, psi collapses to be some random vector in the degenerate subspace. So if I want to get around that, what I have to do is measure the energy, then measure the square of the angular momentum, and that'll pick out a particular value of L, then measure the z component of the angular momentum, and that'll force it to pick out a particular value of L sub z, and then measure the spin, and that'll force it to pick out some value of M sub s. So in other words, making enough measurements of commuting observables will allow you to uniquely specify the state after you've completed all of those measurements. But if you've got degeneracy, in general, one measurement doesn't tell you enough to say exactly what the state is. It just collapses somewhere on the subspace. Then another measurement says, no, wait, now there's a degenerate subspace that's smaller than the whole subspace, where you have a certain value of, say, L squared, and then, oh, but in that subspace, let's make it pick a particular value of L sub z, and so forth. So you can, by subsequent measurements of commuting observables, you can get the system into a state where you actually know the specific quantum state. And there's a theorem to the effect of that basically you can always find enough observables that commute with one another and therefore have simultaneous eigenstates such that you completely resolve any degeneracies. There's a unique state corresponding to any particular set of values of all of those physical quantities. So, for example, in hydrogen, it sounds abstract, but for example, in hydrogen, if you know N and L sub z, and S sub z, so you know the energy, the total angular momentum, the z component of the angular momentum, and the z component of the spin of the electron, that is a unique state. There's only one wave function that corresponds to that. So if you measure all four of those things, bingo, now you know what the actual wave function is, up to a complex phase.
Unfortunately, you had to do 4 measurements.
Oh, sure, right, yes. But, you know, what is a measurement? I don't know, you tell me. We actually, what does it mean to measure something? Well, we've just been saying it as though it's obvious what it means to measure something. That's actually an open question. The measurement, it's called the measurement problem in quantum mechanics. We just kind of leave it unspecified, oh, well, measure the z component of the angular momentum, and why does a measurement cause the wave function to collapse? I don't know. And what exactly is a measurement? I don't know that either, but on the other hand, we know how to do measurements, but nobody has a really formal definition of exactly what constitutes a measurement. And yet we know certain things we do tell us things about systems. So those are measurements, but nobody's ever come up with a nice ironclad definition of what is a measurement. And so we're just not going to worry about it. We're just going to assume, yeah, a measurement. Anyway, yeah.
So I understand if we have the case of different eigenvalues, then psi will choose either or, and then it will collapse that. So if we have two same eigenvalues, so it's degenerate, why can't also psi either get to this or that?
It could, but it could also be any linear combination of them. That's the point, is that after the measurement, all we know is that psi is an element, that psi is one of the state vectors that is consistent. Say we measure the energy of a hydrogen atom. All we know after the measurement is that the state of the system is some combination of all the states that have that same energy. And that's all we know about it. We haven't done enough to say which particular one of those states it's in. Because it could be the one with L equals 1, it could be the one with L equals 0, but that would be the same thing. So we don't know by just measuring the energy which state it picked. We simply don't know yet. And in fact, when we make another measurement, it's not that we're really determining which state it originally picked, we're forcing it to be choosier. Because when we measure what L is, that just forces it to pick some, it collapses to some particular value of L. That doesn't mean it had that before we measured L, it just means that now we're forcing it to have not only N well-defined, but also L well-defined. But we in general cannot know the state of the system before we perform the measurement. Unless we've already performed enough measurements beforehand to have specified the state of the system. But in general, some atom comes along, you don't know anything about it. You measure its energy, well now you know the N value of the hydrogen atom, you still don't know any of the other things about it. All you know is that it's some linear, the wave function is some linear combination of all the states that have that same energy. Disliked the idea of collapse of the wave function so much that he invented the many worlds interpretation to get rid of it. The way you get rid of it is the uncertainty transfers to the observer. You don't know which branch you are in after the measurement. There's copies of you in every branch for all the possible results of the measurement. And And so making measurements splits the observer. Some people think that's cool. It's interesting to think about, you know, if I were thinking about these creatures who think they have unitary, if you will, existences, but in fact they're splitting into copies of themselves, I would find this highly amusing, that these creatures had this delusion of being one thing when actually they were making many copies of themselves. And you can't think of it as like, okay, yeah, I'm the real me, but all the other ones are copies. No, because they're just as justified as saying, I'm the real me, and all the other ones are copies. All of them are, you know, all my future branches are just as much the me of today as one another. So me and the zillions of other branches are just as much the me of some point yesterday. But the thing is, during this conversation, all kinds of quantum events have been happening. There's been quadrillions of copies of all of us made during this conversation. It's this whole cacophony point. I personally, I don't like that. I mean, some people think that's really great. And again, if I were thinking about other creatures, this would be highly entertaining to me. But it stops being entertaining when I think it might apply to me. So on philosophical grounds, I don't like the many worlds interpretation, which has nothing to do with whether or not it's actually true or not. But I don't like it, so I hope it isn't. It's really what it comes down to.
There's one of you that does like it, though.
Probably, but I can't relate to that weirdo. I branched off from, we're all the Borg in this view, you know, so we branched off from that one of us long ago, and we think that they are weird. Yeah, we're the collective, you know, you will be assimilated. Resistance is futile. Actually, it's not it. Resistance is futile. You will be differentiated as opposed to assimilated, you know, because you're going the other direction. And in one sense, you know, well, I mean, I live in the universe that obeys the laws of physics that allow me to exist, so there wouldn't be any of us. I said, speaking of us, if the many worlds interpretation is true, there's no choice. It's the only way we could exist. But we're not very happy about it anyway, if it's true. I'm telling you, okay? We would rather live in our imaginary world where there's only one of us. We're not talking about that.
Anyway. The many worlds interpretation does leave open a very entertaining idea for a talk show. You debate yourself and yourself and yourself
Yeah.
and yourself.
Yeah. Well, it also leaves it, I think I mentioned this before, that if you are a real believer in the many worlds point of view, then if you want to make one of your branches very, very happy, just get somebody to agree to pay you to play Russian roulette. You know, so $1 if you live once, $2 if you live twice, $4 if you live, you know, and so on and so forth. The geometric progression there, you know. So by the time you've shot and missed 20 times, you're fabulously wealthy as a result of this. Now, most of your branches end up blood splattered all over the wall, but who cares? Because one of them shot himself 20 times and won every time. And in principle, okay, I'm going to do it 1,000,000 times. So one of them is going to live through 1,000,000 times, right? And also, I don't know if this is quite true or not, but it's at least conceivable, you know, one of us got into the other room, holy crap! You know, they actually tunneled, right? So, it's weird. Entertaining, but I still don't want to be us. I want to be me, damn it. It's just the way I feel. I gotta be me, and only me, or something like that. Okay, one more thing. 5. This is it. The state vector evolves in time according to the Schrödinger equation. And that's it. According to Schreck. In other words, I h bar d dt psi is some operator h applied to psi. Except when we make measurements and it collapses randomly. So put it together, that's quantum mechanics, and gosh, we're done. No more is necessary except for the details like solving for the hydrogen spectrum, you know, and stuff like that.
Are we going to do it?
Oh yeah, yep. That's our next topic, is quantum mechanics in 3 dimensions. And then we're going to be like, look, it's the angular momentum operator. And look, we can make L plus and L minus operators, kind of like A plus and A minus, that raise the states. and lower the states. And so we can do this clever algebra to solve the angular momentum problem without having to use a differential equation. It's going to be like a harmonic oscillator. It's going to be great. It's going to be exciting. It's going to be wonderful. And it's going to be not today. So we're done.
Thank you. Just instead of saying get more sleep, saying make sure that there's no idiots coming apart.
As I told you, you can solve the problem.
Yes.